We'll wait for 2 more minutes and then start the session. Good evening, everyone. Hope you had a wonderful day today. So, welcome to week 3 problem solving session for the course Natural Hazards. I'll share the PowerPoint presentation. So, just let me know if it is visible to you. I hope you can see the presentation and hear me clearly. So, let's begin. So, for those of you who are new to this problem solving session, so I'm Anchana. I'm the TA for this NPTEL course Natural Hazards, which is taken by Professor Javed and Malik from IIT Kanpur. So, first of all, we'll start with the internal structure of the Earth. So you might be familiar with this, but then I thought it would be better to discuss this briefly so that in the upcoming parts it'll be a bit easier for you to understand. Since we'll be discussing mainly plate tectonics and different kind of faults in today's session. So the Earth's interior. So as you know, like all those things that we see on the outside of the Earth, which is very much visible to us, that is like the mountains you see, the rivers you see, mm, all kind of features. Some big crater you see. So all these things you see on the surface of the Earth. So you know what is present on the surface. But then you do not know what is happening inside the earth. So, seismologists in particular studied the interior of the earth, and and according to them, the earth interior can be primarily divided into three. So, that is the crust, the mantle, and the core. So, the crust is the outermost layer, mantle is the innermost, not innermost, the middle layer, and core is the innermost layer. So this classification of crust, mantle, core, that is the chemical classification based on the chemistry. So primarily the crust is composed of silica rich minerals and then rocks made from such minerals. So and silica and aluminum. So mostly it has a Cl. People say it as Cl composition. So silica and aluminum is predominant in the crust. When you come to the mantle, it is primarily silica and magnesium. So silicon is there, magnesium is there. So these element like minerals containing these elements are more. And then finally, when you come to the core, you have the Ni composition or the nickel and iron composition. So it's predominantly metallic in nature rather than containing minerals like the crust or the mantle. So the crust, as I said, that is the outermost part of the solid earth, as you can see in this image also. So this crust itself can be divided into two, that is the oceanic crust and the continental crust. I've just put the abbreviation here, so you have to understand OC is the oceanic crust and CC is the continental crust. So what it essentially means is that oceanic crust is the part of the crust which comprises of the ocean floor, like the ocean as such. So that is the oceanic crust, and continental crust, as the name suggests, the continental part of the crust. So we call it as the continental crust. So if you remember from the previous discussion session, so I had said that oceanic crust, it is dense. So there's some interesting feature of these two crusts when you look at it. So what you see is that if the uh, the oceanic crust is like 5 to 10 kilometer thick, and the continental crust on the other hand, it is like approximately like 35 to 40 maybe, so kilometer thick. So you can see how the thickness is different. However, when you compare the two, so this is the oceanic crust and this is the continental crust. So when you compare between the two, the oceanic crust is denser, although it is less thick. So density of oceanic crust is high. So density, if you need to understand it in a more simple term, so you can say it is on the heavier side and the continental crust is on the lighter side. So this is less dense. The continental crust is less dense. So this is the classification of the crust part of the Earth's interior. So that is what is written over here. Now the mantle is, as I said, that is the middle layer of the Earth's interior. So that extends from the crust bottom to nearly 2,900 kilometer deep. So if this is the crust bottom, then it will go to say approximately 2,900 kilometer deep, and like the crust, this this can be classified as the upper mantle and this is the lower mantle. So in this case, I would like to tell about the asthenosphere. So the asthenosphere, I think you might have heard Sir discussing it in his lectures also. So the asthenosphere is the part of the upper mantle. So we have the upper mantle and the lower mantle. Okay, so that is the mantle as such is divided into the upper mantle and the lower mantle. This is the middle layer. Okay. So what you mean by asthenosphere is the part of the upper mantle which is just below the lithosphere and which is involved in plate tectonic movement. So this asthenosphere, unlike the crust or the other part, it is a bit more liquid kind of nature. So it flows basically. Asthenosphere is a semi fluid, you can say. So it flows. So this asthenosphere is the part on which the lithospheric plates or the plates, the ones we were discussing in the last class also, that is moving. So if it were rigid, these plates would not have been able to move. But because asthenosphere is partly fluid in nature, so that is the reason why the plates move. If you have any doubts, you can just stop me and you can ask me. Please don't hesitate. Like for some of you it might be very basic, and for some of you it might be altogether new. So I don't mind explaining it again. So don't hesitate to ask. So as I said, so asthenosphere is important because we will be discussing about the plate tectonics in the upcoming slides. Of course, we had a brief introduction in the previous class. So still I thought it is important to recap it once more. So that is the thing regarding mantle. And then when you come to the core, that is the centermost part. So you can just imagine this to be, kind of, uh, it looks like a layered cake kind of thing, or else you can just imagine a fruit with a seed inside. So that seed is the core. That way you can think. Okay. So the core is very hot, obviously. So as you go towards the center of the earth, it is very hot, and the pressure is also very high. So very hot, very dense center of our planet, and unlike the crust and the mantle. So crust and the mantle has a lot of minerals. However, the core is made almost entirely of metal, which is specifically iron and nickel. So that's what I said. It has a Nifi composition, nickel and iron. So it has a more metallic, composition rather than containing minerals of different types. So that is a brief introduction regarding the internal structure of the earth. Now we will go to the plate tectonics part, which we had discussed, like a part of it we have discussed in the previous session, but those of you who couldn't attend it, it will be a new thing for you, and for those of you who attended it, it will be a recap. So anyway, so as I said, the plate tectonics involves lithospheric plates. So what is the lithosphere? So lithosphere, now since you know that about the crust, so the lithosphere is the crust plus the uppermost part of the upper mantle. So it basically constitutes the, like, this entire thing is what is called as the lithosphere. So lithospheric plates is basically encompassing all these parts of the Earth's interior. Okay. So the lithospheric plates, they are basically large broken pieces of lithosphere that move relative to one another. So they move relative to one another because, see, the lithospheric plates movement is not, you cannot see it in a day or two or even in an year, but rather it happens over a long period of time. So thousands of years or millions of years. So in that scale, if you see, you can see a significant movement, but on a day-to-day basis or a monthly basis or on an annual basis, you cannot see that difference. So the processes which are associated with the creation, the movement and the destruction of lithospheric plates are collectively known as plate tectonics. So plate tectonics, the name itself, from that you can understand that it is something related to lithospheric plates. So what is it related to? The processes which is associated with the creation, movement and the destruction. So something is getting formed, something is moving, something is getting destructed. So that something is basically the lithospheric plates. So that entire thing, if you take, that is here plate tectonics. So creation, movement and destruction of lithospheric plates encompasses plate tectonics. So this image I had shown in the previous class also. So this basically shows you the plate boundaries, okay, the different plate boundaries that is found across the globe. So as I said, you have convergent plate boundaries, you have divergent plate boundaries, and you also have the transform plate boundaries. So I think first we'll discuss this and then I'll show that map once again, so it will be easier for you to understand. So the results of plate tectonic forces are most evident along narrow zones between plates where most movement occurs. So you cannot, if you are looking at the center of a plate, okay, like some, let's say the Indian plate for that matter. If you're standing in the center and then you're looking around, you will not see that change, if it has moved ahead or it has gone behind or whatever it is. So you know that the Indian plate is pushing against the Eurasian plate. So that movement, if you have to identify or if you have to, measure, quantify, then you have to go to the plate boundary. So the plate boundary in this case is the region where the Indian plate and the Eurasian plate is colliding. So the results of such plate tectonic forces you will only see in this narrow zone where the collision is happening in this case, or in some other case where subduction is happening, or where offset is happening, whatever the case may be. So wherever that narrow zone where the results of plate tectonic forces are most evident, where the most movement occurs, that region we call it as the plate boundaries. So that is the boundary. There are mainly three types, as I said. So we have the divergent boundaries, then we have the convergent boundaries, and then we have the transform boundaries. So as the name suggests, divergent boundaries is when two plates move or diverge. The name itself tells you something is moving away. So they move away from each other. That is the divergent boundary. Of course, I can tell you this in detail in the upcoming slides, but then the basic understanding is this. So it is diverging or it is moving away. Convergent plate boundary is when this is moving towards each other. So this can be either collision boundary or it can be a subducting boundary. And transform boundary is when there is just a horizontal movement and there is no extension or compression happening. So in this case where the divergent boundary is, we have the extension motion, right? So it feels like something is being pulled apart from either direction, and in this case something is coming towards each other. So this here you have a compression, but here you only have that motion present, either like this or either like this, but then you don't have any other movement happening in case of transform boundaries. So the divergent boundaries you can see here. So that is new crust is generated as the plates pull away from each other. So this is basically what I meant to say. So this is two plates are moving away from each other in this image, if you can see. So the initial case, so this is like the process is happening. So initially, if you look at this thing, it would have been like this, okay? So initially, let's say it was intact, and then some weak zone developed over here and it started moving away. So this is the first case, okay, when nothing was happening. Once it started moving away, so something is getting stretched, something which is very much a solid structure is getting stretched. So it will not just move away just like that very smoothly, rather some cracks will be formed, right? So that is what you can see over here. So the step kind of thing, this is known as Horst and Graben structure, but you don't need such terminology right now. Only thing you have to understand is when this is moving like this, these structures form, and in the upcoming slides I'll be discussing, but now also I can just tell you the faults, the weak zones that are formed over here are normal faults. I'll also discuss when I'm discussing the different types of faults, but I thought it would be better to tell it over here also. So this is what is happening. This is moving away from each other. This center zone is breaking up apart. So you have this particular structure going on over here. That is what you see in the figure also. So this happens. So when this gap is built, okay, some gap is coming. So what is happening is the magma that is present beneath this lithospheric plate, that will come up, it will pour out, and then it will solidify. So this on a large scale when it happens, that is when you say that the oceanic crust or the ocean floor that is being continuously destroyed, and at the same time it is regenerated. Like it's not completely destroyed, constant regeneration is taking place. So that is new crust is generated as the plates pull away from each other. I'm once again telling, like, if you have any kind of doubts, please feel free to ask me. I'm not sure if you're familiar with these topics. That's why I'm again and again repeating this. So next comes the convergent boundaries. So convergent boundaries, two plates which are farther away or which are close by, whatever be the case, they are moving towards each other. So when two plates like this move towards each other, two things can happen. Either, or rather the thing is, first it will subduct if Okay, I'll tell you the condition. So subduction can happen, collision can happen. So let's just imagine this is a oceanic crust. So you have water over here. Okay, so this is the oceanic crust. Some bit of land is over here. So this darker part is the land. Okay, so this is one plate coming in this direction, and then you have a continental crust which is coming in this direction. So first, when this part of the lithospheric plate meets this continental part, this oceanic part meets the continental part, as I said, since it is more dense, the oceanic crust or the oceanic plate that will go down or it will subduct and beneath the continental crust on the right side. So the first subduction will happen. So once this keep on happening, and at a point what happens is that this entire ocean part or the oceanic crust part goes beneath this continental crust, and then this part of the continent and this part will have to meet. So since they are of comparable density, they will no subduction is going to happen. Rather, they will collide with each other, and an upward kind of folding, all those things happens, like deformation happens, and then you have a very good example like the Himalayas forming in such conditions. So in case of the Himalaya formation, this ocean was the Tethys Sea. Like the water body that was present was the Tethys Sea. The Tethys Sea completely, got subducted, and then the land in the Indian plate and the Eurasian plate collided with each other. So that is how you have two kind of uh, processes happening in case of convergent boundaries. Then comes the transform boundaries. So in this case, so the previous case, in case of divergent boundaries, a crust is getting generated, a crust is getting built. So something is happening over there. In case of convergent boundaries, collision is happening, subduction is happening. In both cases, something is getting lost or destroyed. But in case of, oh, I'm sorry, I have not corrected this, but in this case transform boundaries, only thing is that there is nothing is getting generated, nothing is getting destroyed, rather they are just sliding past each other. So some offset might be there, some change in position might be there, but basically you don't see anything happening to the lithospheric plates. And this is mostly like on a large scale, it is observed between two mid-oceanic ridges. So I'll tell you what that is. So with this idea in mind, I'll just show you a video which basically explains what I just said, but I think visual memory is more easier to understand rather than hearing something. So I'll just play this for you. If it's not clear, you can ask me. So I hope that is clear to you. I had explained these trenches and these volcanic arcs in the previous session. That's why I didn't discuss it again. So by seeing the video, or if you have any doubt, you can ask me if there is any confusion regarding that. So this brings us to hotspots. So as I said, uh, the volcanoes that form in case of the subduction, you might have seen. So we have volcanic arcs, we have island arcs. So you know from where this, it is happening when two plates are coming together and then melting is happening. So that is how that volcano is formed. But hotspots are special cases. So why they are special is because American geologists, like they were discovered when American geologist James Dwight Danner. So this is like I have taken the material from Professor Malik's lecture. So I think you might have read it also. So the American geologist James Dwight Dana in the 19th century. So that 19th century means like this 1813 to 1895. So in that time he observed that the age of extinct volcanoes is that those ones which have stopped erupting. There is no particular activity going on, and then over time they are getting eroded. Eroded means the surface is getting deteriorated over time. So such extinct volcanoes. So what he saw is that they were older, or than the active volcanoes that are currently present, especially in case of the Hawaiian island chain. So for those of you who know it, or in maps, if you've seen, the Hawaiian island chain is, as the name suggests, islands are like this. So what Dana observed is that, for instance, let's say this is a volcano. Okay, so this volcano is older and this volcano is younger and it is active. So this is extinct also. So what he understood was that this volcano, which is present, which is extinct, that is older when compared to the this one, which is younger and more active at present. So that he observed in the 19th century. Then after years later, so you can say like 1960, so which means you have complete century has passed, right? So 19th century, and then you come to the 20th century. So in 20th century, J. Tuzo Wilson proposed that a long-lived hotspot lies secure deep in the mantle beneath Hawaii. And a hot bind. So basically, I don't think I should be reading this out. So basically, what he was suggesting is that, let's say this is a a landmass. Okay, so a lithospheric plate for that matter. Let's say this is the one. So what he's saying is that in all the other cases, this volcanoes are formed when this movement is happening, and it is happening within the plates, right? So in this case, however, volcano is not found on the boundaries. Rather, most of the time it is seen in the uh, more interior of the let's say the plate. So that is a very confusing thing, because we know where it is present in case of the convergent and the divergent boundaries, but in case of in this case we don't know where it is, like how it is formed. So based on Tuzo Wilson, what he is saying is that if this is a landmass, and what he is saying is we have uh, a very deep seated mantle plume, we say. Like mantle plume is basically you have the mantle rock coming up, the buoyant means less dense mantle rock coming up, melting, and then coming out of the like coming through the crust. So that is such a situation is what is being explained over here. So a hot buoyant plume of mantle rock continually rises from the hot spot. So this is called as a hot spot. So in this case, what basically they're suggesting is that this one is stationary. It is not moving. It is stationary. It is wherever it is present, its position is not changing. The lithospheric plate above it is moving ahead. So basically, if this was present over here, and you have the lithospheric plate over here, so let's a volcano is formed over here. then this lithospheric plate will move ahead. So then the part of the lithospheric plate following it will come in this position, and again the volcano will be formed over here. So basically that's how this chain of volcano is formed. I have a good image in the next slide, so I think that will help you understand what I'm trying to convey over here. So this, if you see, okay, now, so this is the motion of the Pacific plate. Okay, so the plate involved in case of the Hawaiian island chain is the Pacific plate. So it is moving in this direction, and you have a chain of volcanoes present. So you might have heard of, maybe you might have heard some names, maybe you're not familiar with it, but yeah, anyway. So what Tujo Wilson was saying is that the Pacific plate is moving ahead in this motion. So but the hotspot is staying intact. So as you go farther, so okay, I think I have explained it a bit different, but anyway. So as you go farther away from the plume head, where the source of the magma, it becomes older, and wherever the plume is currently present, you have an active volcano which is younger. So that is the idea conveyed. I think this can be discussed in much more detail when you have a lecture on the volcanoes, which is again a natural hazard. So in that session, I can maybe figure out some videos for those of you who couldn't imagine this properly. So that way we can go ahead. So this brings us to faults. So faults are basically fractures in the crust along which rocks on one side move past the other. So I have an image over here. So from this and the description that I've written, you might be able to understand. So you can see, if you look clearly, you can see a line going through like this, right? It's not exactly a line, but yeah, a thin boundary is there. And you can see, if you look at the movement, you can see this part of this block is going up and this part is going down. So this thin line which I'm talking about, that is the fracture, some weak part of the crust. So that fracture in the crust, along which, so along this line that I have drawn over here, this part is this part is going down and this part is going up. So here we have this is essentially called the fault or fault line, you can say. So inactive faults are there and active faults are there. So inactive faults are those which have not moved for a long time. So maybe once the movement might have happened and then it has stayed intact. So those for not once, it might have happened for a long period of time. Anyway, now when you're looking, there is no significant movement. So then you can call it as an inactive fault. And those in which this movement is constantly taking place, people study it by keeping this GPS instrument. So you cannot go and measure it with a scale, right? So what people do is that they keep position GPS instruments in different places where they know the fault line is present, and then like periodically they will take the data and then they'll see on what rate this movement is happening. So that really helps people, especially faults are important because it is very important to understand in case of the natural hazard, that is the earthquake. So that way people, definitely seismologists study the movement of faults in order to understand when like whether you should expect an earthquake in the near future, or like if earthquake will happen. All those things can be figured out. So the classify this faults can be classified based on the movement of rocks on either side of the fault. So I had shown an image in the previous one. So if I do it diagrammatically, what I'm trying to convey is, let's say you have a section like this, layers of sediments or whatever, some layers are standing like this. Then you have a weak zone or a fracture or a fault line which is present along the center part. So this is the first case, and then when movement happens, what is happening is this part goes up and this part comes down. So that is the movement. So based on this movement, that is what I am trying to say. So based on the movement of rocks on either side of the faults can be classified into dip slip faults and strike slip faults. Dip slip faults are those in which you have this, you know, angle present, and the based on the direction of slip, that is what I have written here. So based on the direction of slip, like in which direction that movement is happening or slipping is happening, and the angle at which it is happening. So you have the normal fault and the reverse fault, and then you have the strike slip fault, in which it is not happening along an angle, but rather it is a horizontal movement which is happening. So that is basically, it can either happen in this way, this part is coming over here, it can either go this way or the other way around. So I'll tell you what normal and reverse faults are. And you also have oblique slip faults, which are a combination of dip slip faults and a strike slip fault. So it has a horizontal movement as well as it has a vertical movement. So this image will tell you what each of the faults are. So you have a reverse or a thrust fault, which is a kind of a dip slip fault. So in the reverse fault, this part which is going up, which we call it, I don't think sir has taught you that way, but anyhow, this is the hanging wall and this is the foot wall. So foot wall is the part of the that block on which the hanging wall is moving. So the hanging wall moves up and the foot wall moves down. If that is the case, then we call it as a reverse or a thrust fault. So that movement is shown in this case. So the hanging wall is moving up and the foot wall is moving down. In case of a strike slip fault, you have a horizontal movement. So if you look at this image, you can see the fence has displaced, right? So earlier the fence was together like this, and then when this movement happened, this part of the fence went ahead and this part came behind. So initially it was like this and this went ahead and this came behind. And then normal fault is just the ulta, like just the opposite of reverse or thrust fault. So in this case, the hanging wall is coming down and the foot wall is moving up. So that is the normal fault. I hope you are understanding this. If you are new to this topic, please tell me, because I don't know in how much detail I should go. So I'm just touching upon the major general points that are required for you to understand the topics coming ahead. This brings us to elastic rebound theory. So basically, elastic rebound theory explains the phenomena which is known as the earthquake. So the elastic rebound theory, it's basically, you have to understand is that rocks have a elastic nature. So that is, they can bend when a force is applied. So elastic, you have a rubber band in your hand. So initially, let's say it is in this shape, okay, and then you just stretched it in this direction. So the shape becomes like this, something like this, and then you release it. So when you release it, it comes back like this. So that is basically what you understand by elasticity. So rocks have an elastic nature. So they can bend when a force is applied, and when that force is removed, they will tend to come back to their initial state. So what happens is that, let's say we have a fault like this, okay, a weak zone, a fault line like this. So what it says that rocks near a fault are slowly bent elastically as crust moves and energy gets accumulated. So you can just imagine it like this. So let's say this is the fault line and initially the layers were standing like this, okay. So this fault line is a weak zone, so movement is happening. So let's say this region is going up and this region is coming down. So when that movement happens, it's not like it is going to break and go up. So in the initial stage, it will bend like this. So instead of a straight line like this, you can see a bend forming like this, where the fault movement is happening. So that is what it is saying. So it is slowly bent elastically as crust moves and energy gets accumulated. So when you can imagine, right? So let's say you are wearing this rubber band on your hand and then you're stretching it like I said. So when you're stretching it, slowly energy is getting accumulated. The moment you release it, some of you might have tried it, which is like anyway. So you know how painful it is, right? When it comes back and hits your hand, that much of energy has accumulated, because of which once it comes back, it is very painful. So it's kind of the same case in case of the elastic rebound theory explanation for the earthquake. So what is happening is this movement along this fault line, initially it is getting bent, like it is getting pulled, it is getting bent, and as a result of this energy is getting accumulated. Then a point comes when it cannot withstand this, like a point comes when that that maximum saturation has happened. So then a sudden release of energy happens, in which in the form of earthquake, in which this sections just separate. So instead of this bend, basically you will finally have something like this. So this part is gone completely up and this part is gone completely down. So the rocks rebound to their original undeformed shape. So for somebody seeing this place for the first time, or maybe if they're just seeing this section, they will not understand that something like this big has happened over there, because they're seeing intact layers. But then when you come to this fault line or this fracture area, that is the time when you understand that some this movement has happened, and that the rocks had bent and then they have rebounded to their original shape. So this is the elastic rebound theory, which is an explanation for how earthquakes are formed or generated. So first that stress is applied, then the strain is accumulating, and then a sudden release of energy happens, and that sudden release of energy happens in the form of an earthquake. That is how an earthquake is generated. So here you have basically what I just explained. So you can see over here. So you just keep an eye on this area, like where the pointer is showing. So that red line is the fault line, and you look at the fence. The fence is like a reference point for you to understand how the movement is happening. So the strain gets accumulated along this fault line, and when the horizontal movement happens, so in this case it is a see, you can see that bent, right? So the one which I was drawing also. So first it bent. That benting is shown over here, which is also shown like this. So this structure is first bent, and then the rupture happens. So rupture and release of energy is happening. So that complete release of energy is happening, and both the sides have pulled apart. And finally, this is the thing. So if you look at the rock, that is in the original shape, undeformed shape. But then you can see that deformation and that separation in case of the fence, because the fence broke. I hope that explains what I've been telling you. So this is again a real life example of that offset which is seen in this fence. So you can based on this itself, where the fault line is, right? So this fence has moved in this direction, this fence has moved in this direction. So the fault line will be somewhere in along this, where the yellow line you are seeing. So approximately 2.6 meter, which is not a small thing, right? On the surface you can see that change. So that much of change has happened in the case of San Francisco earthquake in 1906, when earthquake happened on the San Andreas fault. So San Andreas fault is also an example of the transform plate boundary. So this is it's basically an explanation of what I just said. So if you take a graph in which you have stress along the y-axis and a strain along the x-axis, so you look at this and you see that initially till this elastic limit, till that elastic limit, if you increase the stress, that's basically, just imagine you are having a rubber band. So that rubber band is a very good example of this. So the rubber band is like this, okay? So now we are gradually increasing the stress. So the rubber band is being pulled from this side. So essentially the rubber band is going to stretch like this, okay? So that is what is happening. Then the elastic limit is the limit till which that rubber band can stretch. Then if you still pull it, like if again you're pulling it, you're not leaving it, then what happens is that it won't be able to rebound back, rather plastic deformation will happen. So some rubber bands, right, they become loose after some time. So the rubber band which was tight initially, after frequent use it becomes loose. So that is plastic deformation. It's not going back to its initial state. So that is not reversible. So once it becomes loose, like with mechanically you cannot reverse it back. And then further, if you increase the stress, like further you pull it, it is going to break. So that is brittle failure or fault slips. So in case of earthquake, this is what is happening. First some bending is happening, then gradually it is even getting more stretched to the point that it is not going to come back, and then finally that failure happens. So it slips. Fault will slip. So earthquake will happen. So stress are those forces which are acting on a rock, and strain is the change in shape of the rock in response to stress. So that force, when you apply that force, some response is given by the rock, that is known as the strain. So with increasing stress, a rock deforms elastically, then plastically, before ultimately failing or breaking in an earthquake. A completely brittle rock fails at its elastic limit. So that is basically, if the rock itself is not very, its strength is very less, then by reaching elastic limit itself it will fail. But those rocks which are more, has more strength, those you have to only, like it will fail only when it reaches the limit, like the brittle failure limit. So I had asked this in one of your problems, I think in week 1 or week 2 also. So basically the epicenter is the region on the surface of the earth where the earthquake has originated, but the actual point of origin of the earthquake is known as the focus or the hypocenter, which is present in the interior of the earth along the fault line. So paleoseismology, that is the study of prehistoric fault movements. So paleo means past, something in the past. So paleoseismology is when you study the past fault movement. So not the current one that is happening, rather the movement that has already taken place. So the benefit of this is that it helps in understanding the future fault behavior, because you can observe a trend, something is keeping on happening over a time. So if you look back, you can understand how the future movements can be, so you can predict that movement. So this will help us in establishing the recurrence interval of earthquakes, because essentially these fault movements results in earthquake. So if you study the older fault movements, then that will tell you how frequently the earthquakes are happening, and then you can actually predict, although not very accurately, but then still this helps you in understanding or quantifying when a future earthquake might happen. This is basically, like you can understand from the offset seen in sediment layers. So here you are seeing multiple offsets. So this is basically a schematic diagram of a trench dug across an earthquake fault. So this fault line, this red line that you're seeing, is an earthquake fault because multiple earthquakes has happened in this region. So what they're showing is the relative displacement of layers offset by movements at different times. So these 1, 2, 3, these are different offsets that has happened in different times, not like they happened all together. One was the oldest, and then comes two, and then comes the third one. So during the first earthquake, that is this one, the offset, uh, the top of the gray layer, if you look, you can see it has come down, right? So during the second earthquake, then the offset is like this. So this much of difference is there. This part, earlier it was over here, and then it came down, or rather you can say this went up, either way. So that change you can see, right? And this one, it should have, this one and this one should have been together, and this one and this one. So that changes, this offset is less actually, if you take a look at that compared to this one. This 2 is the offset during the last earthquake that is shown over here. So based on this movement, people can just study how much that movement has happened, and based on that, they can predict like how frequently or in how much time a new earthquake can happen in this fault. Then comes seismic gap. So segments of a major fault having less earthquake activity than neighboring segments. So if you look at a like similar image, let's say, okay, so in this case you can see that fault movement has happened like this. So you have multiple offsets over here. So but in some cases that might not happen. Like there will be segments of a major fault where earthquake activity was less when compared to its previous or earthquakes prior to it or after it. So there is a gap in between. So this are most likely areas for future fault movements. So in future, the earthquake can happen in such seismic gaps. So seismologists, they also study a complete fault line, and they identify such gaps, and then in that way they can warn the people that this is a potential site, region where uh, a future earthquake can happen. So a seismic gap, here you can see in the historic earthquake pattern along the San Andreas fault. So this is the San Andreas fault, and they studied the historic earthquake pattern, and then they identified this seismic gap, which is depicted by this blue line, and these are earthquake events. So this is the seismic gap that they observed. Southern Santa Cruz Mountains gap, and then you have the San Francisco Peninsula gap. So this region did not experience much of the earthquake. So they predicted that the Loma Prieta region might experience the earthquake, and then uh, the earthquake did happen in 1989, and that's how. So basically, it's always better if you can identify such seismic gaps. So earthquake can also migrate along a fault over time. So it's not necessary that the earthquake happens only in one place. Rather, it can migrate along the fault line if the fault line is very huge. This brings us to the problems of for this week, and then I'll also discuss the week 2 assignments, so that if you have any doubts, we can just clear it over here. So the location, like those of you who know, please give me the answer. Like you might already know it, but still. So the location of maximum damage caused due to an earthquake is at. You have the options here, same everywhere, epicenter, focus, none of the above. Yes. So as I said, the epicenter is the point of origin of the earthquake. So you can see as you are closer to the epicenter, the damage will be the most, and then as you go away from it, the damage will be slightly lesser. The highest magnitude of the earthquake in the collision zone, such as the Himalayan belt, will range between, like, this is just if you can make a guess, like what will be the highest magnitude of the earthquake in the Himalayan belt. Yeah, like 6.5 to 7.5, like earthquakes has happened, but even 7.5 to 8.5 magnitude earthquakes has also happened in the Himalayan belt. So that is the highest magnitude as of now. Of course, it can increase or whatever, but this is the current one. So you are also aware that recently you are having this multiple earthquake events happening in Nepal and all. So that is mainly because this is a very active region where this motion is happening. Then the isoseismal denotes contour or line on a map showing an area experienced what, like, from this options that is given: similar arrival time of an earthquake, similar earthquake intensity, similar p wave velocity, similar damage pattern. Yes. So it is the similar earthquake intensity. So that is basically isoseismal. Iso means same. So that itself tells you similar of something, and seismal is basically related to earthquake. So similar earthquake intensity is what you understand by the isoseismal contour or line on a map showing an area experienced. So, dash is the part of the ocean floor where mantle plumes bring the magma and down, let down them on the ocean bed according to the present magnetic behavior of the earth. It's basically there is a part, yeah. So the answer is mid-oceanic ridges. So this you might also remember from the previous lectures, as I said. So you have the mid-ocean, like basically to the this part of the oceanic crust which is moving away, and then you have the ridge forming like this. So this is basically the ridge forming. So this is the part of the ocean floor where the mantle plumes bring the magma, lead them down the ocean bed based on the magnetic behavior of the earth. So basically, if you study this different uh, regions of this crust, you can actually understand how the earth's magnetic behavior was, because it contains such magnetic minerals and elements present. In the thrust faulting, dash move over the dash in ongoing deformation. So thrust fault, what is the other name of thrust fault? So yeah, so reverse fault. So can you give me the answer? Like what happens during a thrust faulting? Something moves over the other. So I had mentioned about hanging wall and foot wall. So what moves over or on top of the other? Yes. So the hanging wall will move over the footwall in a ongoing deformation in case of a thrust fault. So thrust fault is not actually exactly the reverse fault. Like the movement is same only, but normally thrust fault in a small definition you can say it is a low angle reverse fault. So the angle is less in that movement. That is all. But in a broader sense, it is basically a reverse fault. So in this case, as you said, the hanging wall is moving up and the foot wall is coming down. Or relative to the foot wall, the hanging wall is moving up. Seismic microresonation is done on the basis of computed peak ground acceleration, which in turn depends on what? Magnitude of earthquake, lithology of the area, earthquake intensity, surface rupture. So if you remember in the previous class I had mentioned, right, in if you take the country India, so in India we have different zones: zone 2, zone 3, zone 4 and zone 5. That is broader zonation. Microzonation is when you take it into even more minute detail, smaller zones. So how do you do it, seismic microzonation? Kind of, but it is basically the lithology of the area. So the thing is, magnitude of earthquake is a factor, but see, seismic microzonation is like you are basically, it's not magnitude zonation. The bigger zones, you can say it is mainly based on the magnitude of earthquake, but when it comes to seismic microzonation, that is done on the basis of computed peak ground acceleration. Ground acceleration is the movement that is happening during an earthquake. So if you remember, in the previous class I had mentioned, right, this movement is basically depending on the lithology. Lithology is basically how that area, like what kind of rock is present, or rock or soil is present in that area. So if that soil or whatever material is present, lithology is present, if that is like very soft, that acceleration will be more. So if acceleration is more, then naturally it is going to affect the people and the buildings and all those things more, right? If in if that area would have been a hard rock region, then that acceleration would have easily dissipated, not causing much of the movement that you experience on the ground. So that is why in seismic microzonation, people consider the lithology of the area. I hope I am clear. If you have any doubt, you can please ask me. Okay, thank you. So the next question, Lesser Himalayas is the region between main central thrust and dash. So it's basically, as I said, the Himalayas. If you know the answer, you can tell me the answer and then I'll explain. Or else, uh, like, are you familiar with this? The main central thrust, the main Himalayan thrust, and all? Anybody? Okay, so I'm not sure if you're familiar with this. So it's basically the Himalayas, it is divided into Lesser Himalayas, Great Himalayas, and the Tethys Himalayas. So this is basically a cross section, a side cross section of the Himalayas. So this is the Indian region. You have the Ganga, that alluvial, that basin is there, and then you have the main boundary thrust. Thrust is basically what the reverse fault that is happening, right? So this is the main boundary thrust. This is the main central thrust. So the main boundary thrust is between the Lesser Himalayas and this part of the Indian Shield, and then the main central thrust uh, is between the Lesser Himalayas and the Greater Himalayas, and then you have all these things. I don't think you have to go to the detailed geology of that. Just you have to understand that if you look at this image, the Lesser Himalayas is the region between the main central thrust and the main boundary thrust. I just saw this question, that's why I put it here, but I'm not sure if you need uh, something in this detail. But if you want me to discuss this in detail, I can do that in the upcoming session. Like if you want to understand this part of the Himalayas, then I can explain it. Now next question is, dash is the surface manifestation of the fault plane that shows the lateral propagation of faulting in the earthquake. So as I said, when an earthquake happens, there is a movement happening inside the earth, right? So if you look at this part, this is the fault line and movement is happening along this fault line. So this thing can be seen on the surface also, right? So what do you call that? What is the surface manifestation of the fault line which shows the lateral propagation of faulting in the earthquake? Do you know that? Okay, I accidentally clicked it. So it is known as the fault rupture. So that is what in that video you might have seen, right? They have shown you the San Andreas fault line. That actually the fault line or the fault plane is in the interior of the earth. But that line that you're seeing on the surface, that is known as the fault rupture. So here you have the image also. See? This is the surface rupture. The fault plane, if you look at this, the dimensional way, so the fault plane is like this. This is the fault plane, and then on the ground you can see it as the fault rupture or the surface rupture. The configuration of opposite dipping faults explains the dash which occurred in the Kutch region. I'm not sure if Professor Malik has explained it in this lectures, or it is explained in the earthquakes part, but still, if any one of you know, you can give me an answer. So configuration of opposite dipping faults. So opposite dipping is basically, if one fault is like this, the other will be like this. One is dipping in this direction, the other is dipping in this direction. That explains a particular phenomena that has happened in the an example you can see in the Kutch region in Gujarat. Okay, so the answer is tectonic inversion. So tectonic is what? Tectonic is like something is happening with this plates, right? So tectonic inversion is basically, I like, if I can explain it to you, it is basically the process where extensional normal faults. Extensional normal faults is because why they are saying it like that, when you have two plates, or rather you have a single plate like this, okay? So you have a plate like this and it has a weak zone over here. So that and this plate is moving in this part of the plate is moving in this direction, and this part is moving in this direction. So extension is happening. So when that extension happens, you have, as I said, you have such structures which are basically depicting the normal faults. Okay, normal fall, because of normal faults only this structure is formed. So tectonic inversion means what? Something is getting inverted, right? So tectonic inversion is the process where such extensional normal faults are reactivated by compression. So it's basically the normal faults are formed by extension, but in regions where you see tectonic inversion, so it's basically that normal fault is there, but it's basically it's not having any, like, it formed and it is there is no movement as such happening, but later on, due to some compressional activity happening around it, these get reactivated. So that is tectonic inversion. Or the just the opposite can also happen, where the reverse faults are reactivated by extension. So it's basically, inversion means what? Something which is happening by one phenomena. In case of this tectonic inversion, it is happening by just the opposite phenomena. So extensional normal faults reactivated by compression, or compressional or reverse faults which are reactivated by the extension. I have an image over here if that helps you. So if you look at this, don't look at the naming and all, just look at the sequence. So you have something like this, okay? And then you can see the weak zones over here. So it is going up, like coming down like this. So here crustal contraction is happening. So first it is compressing. So when compression happens, what happens? You have reverse faults forming, right? Footwall is like hanging wall is moving up and footwall is coming down. So that is what you're seeing here. But then after some time, this region, crustal extension is happening. Like if you are familiar with the geological time scale, you know what Paleozoic is and what Mesozoic is. So almost like several thousands of years later, you are seeing extension in place of compression, and that reactivates these fault. Just the opposite is happening in this case, where first an initial extension is happening and then a contraction is happening. Just the opposite of this one. Now we'll discuss the week 2 assignment. So like if you have any doubts, you can ask me. I will not be providing the options here because you might have already done the assignment. So just give me the answer. So recently, A giant volcanic eruption in the Pacific Ocean on 14 January 2022 led to the widespread damage in adjacent islands. Yes, Kausalya, the answer is Honga Tonga. The next question is with earthquake of equivalent to 7 magnitude could result in surface rupture length around dash kilometer. Can you tell me the answer? You're given the magnitude of the earthquake. You're asked to calculate the surface rupture length. For those of you who have answered this, please give me the answer. And for those of you who don't know the answer, I'll explain it how you are getting it. Does anyone know? You are just given the magnitude of the earthquake. Okay, so then you are asked to calculate the surface rupture length. You know what surface rupture is, right? The thing that you're seeing on the surface, like surface manifestation of the fault line, which is causing the earthquake. Anybody know the answer? If you know, you can give me the answer. Or if you don't, I can explain. Okay. So I think in your options you were given a range, right? It's not an exact answer was given. So normally people calculate surface rupture length using this formula. SRL, I'm just writing surface rupture length. So that is the formula. So that is equal to 10 to the power of 0.69. This is the into the magnitude minus 3.22 kilometer is the unit. Okay, so you are given this magnitude, right? So what you have to do, just substitute it. So you will get 0.69 into 7 minus 3.22. So can you just like those of you who has a calculator or your phone calculator with you, can you just calculate and tell me what this part is, like what the answer is? I just need a roughly, like, if you have a calculator, you can get me the actual answer. So, I've given the formula here, so you can just put these values and just see. Anyone? Okay, so first you will just calculate this part. So this 0.69 into this part. So when you calculate that, you will get it as 10 to the power 1.61. Okay. Now, if this let me just take my calculator so I can get the exact value. So 10 to the power 1.61 is giving you the answer of 40.73. So that approximately, let's say 41. So this is the answer that I was getting from this, and the closest one to your the options given to you was 50 to 80. I know it's very far from this range, but then this is how you calculate the surface rupture length. Like one of the formulas that you use to calculate the surface rupture length. And out basically in such situations, what you can do is if you are given a few options, then you just eliminate the ones that are very much different from your answer. So this 50 to 80 is very a bit closer to the answer that you're getting it. Anybody has any other way by which they have calculated this? Okay, so I hope you're clear how this is done. Like if you have any other formula or any other method with which you have calculated this, please let me know so that I can also share it with the rest of the people. So the next question is, the dash associated with an earthquake is the perfect example towards the hazard estimation and mitigation measures provided, as the estimation of this earthquake results in no damage of the pipeline crossing in the affected area. So you have to give, this is basically an example that was discussed in your week 2 lecture. So you have to give me the name of the fault in this particular case. That is what I'm asking you. I'm not giving the options because you've already done this assignment, that's why. So there was a fault in some place, which is a perfect example, like, people, the planned the construction of this crude oil pipeline in this area according to that fault. So because of which it kind of proved that mitigation measures, if properly implemented, then earthquake damages can be reduced. So what is the name of that fault? I had discussed this in last week also. Okay, you might have forgotten the thing. So, yeah, the answer is Denali fault. So, if you remember, the people over there, so they kind of, the seismologist and like the official people, what they did is when constructing a crude oil pipeline, they constructed it along this Denali fault. Okay, along, like let's say this is the Denali fault. So what they did is, instead of, if they had created that pipeline across the Denali fault, for instance like this, when the movement occurs along this fault line, this would have broken. This pipeline would have broken. So in order to you know avoid that damage, what they did is, instead of creating it across, they created that along the Denali fault line, like this. And some other modifications they made in such a way that this pipeline could withstand a very, I don't remember the value as such, but then yeah, a very high magnitude earthquake, and they kind of quantified everything, and that's how they built this pipeline. So basically, when a earthquake occurred, according to their estimation, so this pipeline was not affected. So you can imagine, right, a crude oil pipeline, so if suppose if it was damaged and some other it was very risky, like the pipe that oil would have leaked, and then maybe a fire hazard might have happened. So they kind of mitigated all those things by just doing this, like proper planning and proper construction of this pipeline along the Denali fault. That's why this example is important. Of course, there are multiple earthquakes happening all over the place, but why this particular one was pointed out was because of this. So remember, this is the Denali fault. Landslides in Himalaya are also caused along the dash, a result of ongoing deformation between Indian and Eurasian plates. So just think of all those points that I had mentioned in today's session, like fault movement, type of movements. So The answer is in that. So just try to make a guess. It's basically, it is caused along a fault. But what kind of fault? What kind of fault can you see in the Himalayan region? Any idea? Okay, so if you remember, I had said that the Indian, if this is the Indian plate, let's say IP, and this is the Eurasian plate. So they are colliding with each other, right? They're colliding, and you have the Himalaya over here. So this motion is a compressional motion. Compression is happening. So when compression happens, what kind of fault will form? When extension happens, I had said what kind of fault is forming. So what kind of fault forms when compression is happening? Okay. Yeah, dip slip fault definitely, but what kind of dip slip fault? Like you have two types, right? Like you have normal fault, you have reverse fault, and the other kind of reverse fault is the thrust fault. So what kind of fault? Any idea? Okay. So you have come closer anyway. So the answer is the active faults, and especially in this area we have the thrust fault. Okay. You mainly have the thrust faults present over here because of the compression. The next question is, the reason 2018 flood in a place, that is what you have to fill here, was the most devastating event in the state history. Which state experienced the devastating flood in 2018? Other regions of India also experience flood events, but then this was, in terms of that particular state, this was one of the worst event that has happened in a long period. So, um, no. Uh, you are saying Bihar, right? Okay. So Kausalya is right. The place is Kerala. So, like, of course, Bihar has also experienced flood events. But uh, if you look at the question, what they're saying is, in the state history, if you see, I'm not comparing between states, but in this particular case, in Kerala, if you take a look at the flood events that has happened over a long period of time, maybe 100 years, this was the flood that actually was very devastating. It caused a lot of loss to life and property. So that's why this example was particularly pointed out. Bihar definitely, like every year, it is facing these flood events. So, but in this particular case, the answer is Kerala. Which of the following activities is covered by disaster management before, during, or after a disaster? So, you know what disaster management involves, right? So, please give me the answer. Yes. So, it is all the above. So, basically, when a disaster, a place is prone to a disaster, so the people need to be very much equipped for this reconstruction and rehabilitation, the mitigation measures which should be done before the disaster strikes, and the emergency response when the disaster strikes. Not like during the disaster, and after the disaster you have this reconstruction and rehabilitation. On 25th April 2015, Dash was hit by a a major earthquake with a magnitude 7.8, and the depth from where the earthquake originated is around 15 kilometer. This is a very general question, but still, since it was given in an assignment, I just put it here. Those of you who have answered this can give me the answer, otherwise I can just give it to you. It's a very general question. So the answer is Nepal. Why this is important? Even now, if you ask, then that is because there are very frequent earthquakes that are happening recently in Nepal. So this, I think your week 4 lectures are like it's mainly focusing on earthquakes. So during that time we can discuss this. But then just to just touch upon the topic, when an earthquake event, you can consider it as in like three parts. So you have the foreshock, you have the main event, and then you have the aftershock. So foreshock, the main event is the one in which a devastating large magnitude earthquake strikes. So before that, you will have small earthquakes happening, uh, quite frequently, not at a very large gap, but quite frequently low magnitude earthquakes or maybe a moderate magnitude earthquakes will happen in that region. So most of the time people mistake these foreshocks to be the actual earthquake. So they think, okay, once that is done, it is done. But that is not the case. When such frequent earthquake happen, ideally you should be prepared for a major event. So the major event is the main event. And once that main event happens, which might cause a large, huge loss to life and property, even then it doesn't stop. If that is the main event is very huge, like the magnitude is very high, then you have to expect aftershocks also. So aftershocks might be of lesser magnitude, but that can also happen. This I'm just giving you as an information because recently this not even different northern like parts in northern India, they're experiencing these earthquake events. So this kind of is an awareness thing for you to understand. Floods are the most common climate related disaster, and it includes dash due to inadequate drainage facilities and floods associated with tidal events induced by typhoons, cyclones in coastal areas, etc. So this is basically I'm asking you, or what the question is asking you is the different kind of floods that which are formed due to inadequate drainage facilities and associated with tidal events, all those things. Can you just tell me the different kind of floods? I had just, briefly I had talked about it in the, I think last week session. Seasonal flood is one, then urban floods, right? Okay, so the answer is basically one is seasonal floods, then you have urban floods, and you have flash floods. So if you remember, I had told this that inadequate drainage facilities directly it will that can actually uh, give rise to this not give rise to, because of inadequate drainage facilities, flooding can definitely happen, and it can be the urban floods, it can be seasonal floods, or it can be flash floods. It's basically the thing is, if you have a town or a city area which does not have adequate drainage facilities, just imagine. So and even in a small, not very continuous, but then if you have some okay, some rain happening, and then that can result to urban flood. Seasonal, and when seasonal rainfall happens, then also it is flooding. When the sudden, some other source, also water is coming, then flash floods is happening. So or any event and this area is lacking proper drainage facilities, flooding will definitely happen. The dash region records around 70% of the world's earthquake, measuring up to magnitude 7 or more. This I had definitely, I'm sure I've mentioned last week. Yes, the Asia Pacific region. Oh, so this brings me to that previous, okay, once, or else I'll just explain it once again. I had skipped that map in the beginning to discuss those things. Yeah. So this is basically the reason for the answer for that question. The Asia Pacific region, if you see, uh, okay. So this part, see, you have multiple subduction zones and all those things. So this region is very active. So almost like 70% is earthquakes and such events are accounted for in this region. Other regions are also there, but there you are having this mid-oceanic ridges. So that's not very like, of course you'll have earthquakes, but they're not very prominent as this one. Most of the subduction zones are present in this Asia Pacific region, this region. So the answer is Asia Pacific. Then this is the question. Mountain chains like Himalaya has given lot to Indian subcontinent as, like, some pros of this mountain Himalaya, mountain chain. Huh. But more direct things if you talk about, like some other, that is also fine, but some other things also you can just think about because of Himalaya standing like that. Yes, rainfall. So that is because, if you have a hill or a mountain standing like this and you have a rain bearing cloud, this is a cloud coming over here, definitely this is going to act as a barrier. So majority of the rain will fall over here, and by the time the cloud reaches this other side, it will, like, basically all the rain would have fallen on this side. So that is what this mountain chain like Himalaya is helping us in some sense, because we are getting a lot of rain because we are on this side of the Himalaya. So it controls rainfall. It has provided wealth of mineral deposits and other resources uh, because of the condition in which it has formed. And definitely the rivers emerging from the Himalaya have provided extensive floodplains full of fertile soil. So, as I said, like most of the people, they prefer to stay in regions, especially in the, if you look at the civilizations present in India or even around the world in the past, or even in the present for that matter, people prefer to stay in regions close to this river, basically on the floodplains, because that region is very fertile. So as a result, you can, you can do agriculture, and you, like, basically you have fertile soil there and you also have access to water. So that's why such regions are more populated when compared to other areas. So because Himalaya is present, and most of our rivers like the Ganga, they originate from the Himalaya. So when they bring down a lot of water, as well as they provide us floodplains with fertile soil. So that is all from my side today. So those of you, like, if you have any doubt, you can ask me. I know some of you has joined in late, so if you have any doubt or if you want me to recap the entire thing, that is also okay from my side. So any questions? you're all from different specializations, like your background is different, so I don't know how detailed I should go in. So if you want, please tell me, please let me know, then I can definitely do that. Any question? If you want me to explain something, or if you want to give some suggestion, I'm just like, I'm free, you can just tell me. This map also, I think I had not mentioned it, but yeah, last session I had shown it. It's basically wherever you're seeing that subduction zone, you are having this uh, this earthquakes and the volcanoes present. Basically, the plate boundaries are active regions where you find these earthquakes and volcanoes and as a result volcanic eruptions. Anything else like you want to ask me? Okay, so I hope you have understood whatever I've discussed. If like even if you have any doubt from the previous session and I'm discussing a different topic in the current session, that's okay. You can just ask me. Uh, if time is there, I'll explain it in the same session, or if not, I'll do it in the upcoming session. So please don't hesitate. Like make completely utilize this opportunity to interact so that it is helpful for you, and it also helps me to easily interact with you people. Okay, so I hope things are clear for you. So I guess I'll stop presenting then. So any questions, anything? Cloudburst, okay. So I'll make it a point because I think you have an upcoming session for flood itself because sir will be focusing on that. So I'll explain. You had also asked me to discuss urban floods, no? So urban floods and cloudburst I'll explain during that time. So we can actually continue with the topic. Is that okay? Okay, thank you. So if there are no further questions, shall I end the meeting? Yeah, yeah. If you can access this, I think they've shared you the link, no? I have uploaded a Google Sheet. I think you can access that also. In that, the PPT is also there, and this recording of our discussion is also there in YouTube. So that both links I will be sharing there. That anyway, week 2 it is there. Now week 3 I will be uploading there. If you are not able to access it, please put that in that discussion forum so I know, and maybe, or you can ask this NPTEL, like they can resolve that. I'm sure they have put it up. Okay. Okay. All right. So if there are no further questions, then I'm ending the meeting. Thank you so much for listening to me patiently. And as I said, please don't hesitate. Anytime you can ask me like any doubt. It need not be from that same session. So, yeah, I'm ending the meeting. Thank you.